Alright guys, welcome back to the shop. This video is going to be on replacing the motor out of this Atlas lathe. So that is the new motor I have mounted up. I'm going to go through the steps of how I figured out the math to the right pulley size, speeds, feeds, and what's not, and also show you the old motor that I took off and kind of the basics behind how to change that out and how to get it going where you want it. So that's what we're gonna cover today. Hope you guys like it. And then in upcoming videos, we got our new project coming, the chainsaw mill. So I'll be mounting a 4-stroke motor up to a frame, and then this is going to be beneath it. I got to machine some parts to mount this up, but all in all, we're hoping to have 60-inch chainsaw mill with some homemade bushings and things to get it all working right. So yeah, that's what's coming up. That's what's on the agenda. I got the lathe running, got the tailstock rebuild. I have a video on that, also mounting up this new tool post, and yeah, just some general stuff about the lathe. But now that that's all taken care of, we can get into the real fun project. So hope you guys tune into that and enjoy it. And what my plan is to replace this old motor that died. It started losing power, slowing down, and I could play around with changing the brushes or whatever, but this motor is super old. The insulation on the wiring was cracking, and it's seen better days. So I got a couple other motors laying around. Hopefully I can find one that will fit. But at first I got to do a little bit of math, and I figured I'd show that because it might help people that are trying to figure out what speed for their lathe and whatnot, and surface feet versus the actual motor itself. So alright, let's go over and get started. So tool angles and speeds, which is pretty cool. Just regular carbon steel 1020. I'm not really machining, like, at least I don't plan on right now with this lathe to machine a lot of that. But anyway, so carbon steel, probably more, so between 80 and 100 surface feet per minute. So we'll say, alright, we'll say 100 just to make the math easier. So say we got a 1-inch diameter rod, and then pi times diameter is your circumference. So pi times diameter equals circumference. So 1-inch diameter times pi, 3.1415. That's the circumference. And then we need to figure out what RPM. So question RPM, or we'll do revolutions per minute times that diameter, because this is each revolution. So 3.1415. How many? So that's your diameter times your revolutions per minute will give you how many inches. We're in inches right now. Inches per minute are spinning past that thing. So if we're going to run, and we want this to equal 100 feet per minute. So 100 feet per minute would be 1,200 inches per minute. So if we're going to, so 1,200 inches per minute divided by 3.1415. So we divided it by that. So now we are at 381.9 revolutions per minute will equal our target. So we need 381, and then for 80 it would be 80 feet per minute times 12, which would be 960 divided by 3.1415, so 305 for 100 feet per minute. 305.5 equals 80 feet per minute. So we want that spindle spinning about 300 to 400 RPM, and we're going to do that for the we're going to set it up so we've got 4 options here, so we're going to pick one of the middle options. That way we have some adjustability here, and we can go all the way up. That as you increase that diameter, it's going to be spinning slower, so you won't have to spin. Well, if you have the same speed and you increase the diameter, it will be spinning faster, but for an increased diameter you need to slow the spindle speed down. So 1 inch, I might be doing a little bit smaller than 1 inch, but I don't think I'll be milling a lot of stuff under 1 inch, so I'm going to set that as kind of the faster speed. So if we were over here in this belt selection, a faster speed, we have a bigger pulley spinning a smaller one, so this would be a little bit faster. And so I'm going to set this up so 1 inch will run nicely at this speed, and then if I need to, I can jump to this guy and increase the speed a little more, but I still have 2 selections for bigger material to slow things down. So I think that's kind of my plan. And then we're going to measure these and see the ratio between these, and then we're going to pick a speed that's, hopefully I can find a motor that'll be spinning just about right. So let me grab a tape measure here. So say 7.5 to about 4.5. Mark this down. So on the motor we've got 4.5, 7.5, and then I'm going to measure the other 2. And then we've got 2 inch and 9 1/4 inch, or 9 1/4 inch. And again, this, it's not going to be perfect, but this will get us in the ballpark. So we know that this will be our faster speed here because it's jumping from a bigger one to almost like slightly larger. This is a much larger gap, so this will be spinning a lot faster. So we're going to pick, we'll pick the faster speed that we're going to be running at, because this 1 inch is pretty small. So 9 divided by, or 9.25 divided by 2. So 4.625 ratio on the first pulley, and then 7.5 divided by 4.5 equals a 1.6. ratio. And then after that, so that whatever speed you're having here is going to get stepped down once, and then after that it's going to, same shaft will always spin at the same RPM, but your pulley size, so jumping from here to here doesn't matter. I mean, your shaft's still spinning at the same speed, but as you go from here to here, there's going to be another speed change. So, and in these guys, we've got a 3 inch, 4, a 5, and a 6. And I'm gonna assume these are the same. They look about the same. I can't really measure it, but I'm gonna assume. I think they're about the same. That looks like a 6 inch. Yeah, that looks like about 6. So we have a 3, 4, 5, 6. So we get a little bit of a variable ratio there. That gives you a lot more speed control. So after that we have 3, 4, 5, 6. And then on the bottom we have a 3, 4, 5, and 6. I guess for the drawing aspect, we'll put those all on a shaft together. I know my handwriting's pretty shitty. So 6 divided by 3. We have a ratio of 2. 5 divided by 4. 1.25. 4 divided by 5. 0.8. And 3 divided by 6. 0.5. So, in the position we're at, we are. So I got some junk. That's a radial arm saw and a wood lathe. They're going out of here. With when I unloaded all these new tools, those have been in there, so those will be gone soon. But so we're going to be at the second position for 1-inch stock, like for our approximation that we're doing now. And then hopefully this motor's in the ballpark. We might have to change some things, but this is just to figure out the right RPM of the motor, because that's the unknown at the moment. So if we're in the second position, that means that we are right here. So, and we're going to say that we are on the faster side here too. So whatever RPM of the motor, say it's I think the motor I have is 1725 RPM. It's going to go through a 1.6 reduction. So that's that first one here, because we're on this guy. So a 1.6 reduction. So divided by 1.666. And then after this, it's going to be on the same shaft here, going from 5 to 4. So it will go from a larger pulley to a smaller pulley. So it'll go up by 1.25. So times by 1.25. And I might make an Excel with this in it, and then I could just easily throw in different values for the different options, and then I could run through this. I might do that later tonight. That way I can just double check that my speed ranges are useful for multiple sizes of material. But for the sake of having to do all the calculations, I'm going to ballpark it with this for now. So 1725 divided by 1.666 is 1,000 times 1.25. So, because we're going to divide, wait, 1725 divided by 1.6666. Yeah, so we get slower as we go from here to here, which makes sense. And then we should speed up slightly because we're going from a larger pulley to a smaller pulley. So times 1.25. So that equals 1,000. RPM, or 1,300 RPM. And remember, our goal for a 1-inch piece at 100 feet per minute was 380, or 80 was 305. So we're kind of hauling ass. We're 3 times too fast. Yeah. So let's do one. So say we put it on the other one. So the 2-inch to the 9 1/4, so 4.65. So 1725 RPM divided by 4.625. And then we're going to multiply again by 1.25. So 1725 divided by 4.625. It's 372 times 1.25 gets us at 466 RPM, which is a little closer to our target. And if we hop down to this ratio here, the 4 to 5 is a 0.8, so then we would just substitute that in here. So 0.8 would take us to 1725 divided by 4.625 times 0.8, we're at 298.37 RPM. So that right there is a little more doable. That's a little better in our speed range. So I guess let's just do this. We'll figure out if we're on this 2 to 9 1/4 pulley, we'll figure out all 4 of these and see if that's a reasonable range. Because I also have some carbide tooling. I don't know right off the top of my head what speed, but I know that you can run carbide a little faster, so it might might actually be okay. So 1725 divided by 4.625. So this number is going to stay 372.97. And then we're going to times that by times it by 2 for this pulley here. 700, or I'm going to put this up here, that way we don't get confused, equals 745.9 RPM. And then our last ratio is a 1/2, so 372.97 times 0.5, 186.485 RPM. So sorry, that one's not. We don't need that one. So for these 4 ratios here, 745, 466, 298, 186. So that's okay for, let's see how big of a piece we could put on here and still be all right. So let's say we have a 3-inch piece times pi, 3.1415. So pi times diameter, or diameter times pi, equals our circumference, times our RPM, which say we're at the slower speed, times 186.485. That's going to be in inches per minute, divided by 12. So we're still at 146. That's a little too fast on the slowest setting for a 3-inch piece. So that would be on this setting here and on this pulley here. So our lowest we could go with a 3-inch piece would be 150 feet per minute. And you can divide by 12 in that calculation because nothing's squared. So if you have anything squared in a calculation, you have to apply that factor twice. So, and this stuff here it's called dimensional analysis. It's useful for tons of shit, for pulley calculations, chemistry, lots of different things. That's where I learned it at. So, but anyways, so for a 3-inch piece, 146 still a little fast. For carbide, it's probably okay. Actually, I'm gonna look that up while we're sitting here. Cutting speed, carbide, lathe, tools. So for free machining of plain carbon steels, that's 950 feet per minute, which is very doable on this now. So it's anywhere from 600 to 1,000, it looks like, just off a little quick glance. It's probably different for specific tooling, but yeah, I think that'll be okay. Because like I said, we're still running slow enough on the slowest setting. We're at 150, which is a little bit fast for regular high-speed steel, but it should be okay for, I don't know if I'm going to be doing 3-inch stuff that often anyways. So I think with this setup, we'll be okay with this 1725 motor. So let's go get that motor. So this was a project I'm working on too. I got this hydraulic press, and I hooked it up to it's actually a dump truck reservoir and valve body, and then I got this. I fabricated this little cart here, and I was going to use it as like a little mobile hydraulic unit for the shop, for the tube bender and stuff. But that motor's a little underpowered, anyways. I think it's only 3/4 horse, so I won't feel bad if I pull that motor off of there and put on something else. So here's this little pump. This is still in the mock-up stage. This guy's it's not even mounted. I was just holding it with a vice grip while I was testing this out. I haven't even finished welded all this or bolted it all together. So, yeah, I don't feel bad stealing this motor. I might look at another one too. So let's look at the speed on that guy. Yeah, and I got another project here. It's a flail mower I'm working on, getting it hooked up to run on the skid loader. So I got a little bit of project ADD. So right there, RPM 1725. So, and it's a 3/4 horse, which I don't know how much. I don't know the horsepower calculation for lathe tooling, but that motor over there is very old and not very big, so I'd guess it's about half a horse. I don't think there's a nameplate on it, but I think we'd be all right with something about 3/4 of a horsepower. So let me look through my old motors over here and see if I can find something. So I got two that are 3450. I don't know what this came off of, but this guy is a 1750, so slightly faster than what we calculated for. But this one should work if it works. It's only half a horse, despite its size. It's old capacitor motor. Just taking a look at this thing. There's a little bit of play, but that's kind of normal front to back. But up and down, bearings feel pretty solid. It rolls nice. Not hearing a lot of grinding or anything. Yeah, I think this might be our ticket here. If we're lucky, the frame size, most of these are industry standard. I don't know how old this is, so it might not be, but hopefully the frame size is similar too. Let's give this guy a test, see if it works. So, and this thing can run on, it says, yeah, 110 or 220. We'll just run on 110 because my 220 is over. I'd have to run another 220 plug over here, and I don't really feel like doing that right now for this. But this wire's a little bit janky. I might work on that, but let's just test this guy first. So, this isn't the best way to do this, but it's quick. Just to see if it works. See if it's out of balance or anything. Don't do this at home. So the small end of the plug is always your hot side. Wow, the thing actually runs very quiet, quieter than expected. It very little, a little bit of vibration, a tiny bit, but not much. Yeah, I think that might be the ticket there. Again, it's only half a horse, so I might need something with a little more oomph behind it. But that motor over there, very old. And it is not in good shape, and it was turning. So, and I'm not. Again, this is just kind of a hobby thing. I don't have anything crazy running in here, so I don't think that it'll be too much of a problem. So yeah, let's get this thing. I'm gonna pull the old motor off, and then we'll come back to. I'm gonna measure the plate. I might have to fabricate a plate and make new mounting plate and stuff. Also, I need to check the shaft size. If I'm lucky, it'll be the same shaft. Probably not, but I might be able to run it on this pulley for now with just one size. But we'll see. Alright, so these in comparison. This one's substantially bigger, but it's also way bigger than a lot of the newer motors I have, and it's still only half a horsepower, so I'm not really sure size is a fair comparison. Yeah, this guy was pretty old and pretty rough. I just hooked it up with a quick little. This isn't even grounded. This was just a quickie to see if I can get this lathe on and running. But now that this one died, let's switch these out. I didn't get lucky on the pulleys. This one's. Oh wow, there's quite a bit of slop. That key's loose, or set screw's loose. But yeah, I didn't get lucky. The pulleys, this one's a 3/4 inch. This is like a half or something, so it's a lot smaller. But this pulley will speed things up a little bit. But I think for now it'll work. If it's, I'll redo the math and test the. I have the laser tachometer, so I'll shoot it and see what it's looking like. But worst case scenario, I just got to get another smaller pulley. And also that V-groove pulley might be a little too big too, but that's easy enough to pick up a new pulley. So, all right, let's first things first, get rid of this power cord that was on here. And then this guy's probably going to end up, well, I'll pull out this, actually. Got our farmer wrench here. Yeah. Hey, maybe I'll throw this on the lathe and turn it out. No, probably not, but. Alright, this guy's probably going to the scrap bin. Did good, but it's seen its day. First things first. This definitely been some other motors mounted here. You can tell there's a lot of holes been drilled in this over the years. A lot of weird hardware as well, and that one's missing one, and yeah. So let's dry them off here. Okay, take this off. That's weird. Looks like these are actually brass. Huh. Strange. Alright, we got that cleaned off enough. That mounting plate's quite big. It's actually 6.5. So yeah, that's going to sit right on here. That's going to interfere with those brass. Yeah, we're going to have to take this guy off. Not seized at all. Cool. Brass hardware. Don't see that very often these days. I hang on to those. Alright. Now, this plate's been pretty thoroughly drilled and messed with. I think I might make a new one. Yeah, that guy's clearly been homemade, and it's been drilled, and a whole lot happened to that. So I think I'll just make a new one. That way I can get it mounted up just the way I want it. So the deck it's going to sit on is 5.5. This motor here, this guy's 8.5 wide and 6.5. Just a little shy of 6.5. So we got 8.5, 6.5 on that. And then over here we got 5.5 by 6, 6.5. Yeah. So, yeah, we're gonna have to go quite a bit larger than that one. So we'll see if we can find some plate over here. Here's a piece that was torch cut. So yeah, we got 7 there. I think this will be the ticket here. And I got an abrasive cutoff, but and I got a table saw or a vertical bandsaw, but the bandsaw has been having some trouble, and I don't have the guide quite figured out yet, so it still cuts a little crooked. And this is a little bit thick for the chop saw. I have to cut it twice, and it's kind of hard to even up. So, and this has already been torch cut once. I might just torch cut it again, and then I'll even everything up with the grinder. And it's not entirely crucial how, you know, this isn't a machine part or anything. Okay, so we got 3/8 bolts that are going in there. This thing has to be able to slide, and want a little bit of room on these because they're not exact, so I'm drilling a 7/16 hole plate. Alright guys, so I've got a quick plate made up here. Motor fits nicely. Now, all we got to do is got plate cut, drilled and everything. Fits nicely. Now we just got to go over, lay it out on the lathe itself, and then we can check out kind of how this is going to all come together. So I think what we'll do actually is we got one mounting hole here. It's kind of going to be hard to see, but this mounting hole here is the same hole for the plate to sit on, the lathe. So I think we'll actually match that one up. Over here, this one hangs off. And then this guy over here also hangs off. And so does this guy. So we can mount those. That'll give you a little better view. But this one here, and that one there will all mount separately. We'll just thread this plate, thread it, bolt into there, and then this guy will share this hole here. And that gives our belt. My belt has to run slightly angled out, but also I think I got to get a smaller pulley for that too. But it'll run a little bit of an angle, but it'll be able to handle that. And then we can also run this guy off with just one pulley for now, until I get a 2-step pulley there. Yeah, I think that ought to work. Alright guys, so I'm over here tapping this plate, got it cut out, and got the holes marked on the lathe. And I was just going to make a quick note about tapping holes. Because like anybody else, first, you know, when I was first learning how to tap holes, I kind of struggled with getting straight holes tapped. And I used to just like go find drill bits that I thought were the right size and, you know, drill the hole and then tap it. And I broke taps and all sorts of stuff. Didn't know what I was doing. But kind of over the years I've learned the best thing to do, get yourself one of these charts. Helps you for thread identification of pitches and different threads. And also, if you look at it, we've got, here, I'll bring this up. You've got, like we're working with coarse thread right now. So it tells you your tap size, threads per inch, what size drill to drill the hole to tap it, and then also a clearance drill of what size will allow you to pass the bolt through. So make sure, because this really helps, because you know you got the right drill bit, you know you got the right size hole. And then also a note on taps. I've got some old taps that were my grandfather's, and like any other you know, high-speed steel tap, or these are just a huge huge improvement over the cheap big box stores taps that are just carbon steel, and they break, they don't cut threads well, they really struggle, and it's just honestly not worth, I mean, it's like anything else. You put the money in, and you know, whatever you pay is what you're going to get. So definitely get yourself some good taps. And then also the different kinds of taps. So starting taps have blunted threads on the first several. It's like 6 or 7, and then I don't know what the middle tap is called, but there's only blunted threads on like the first 3, and then you have bottoming taps that are threaded all the way, full size threads all the way through, and they only have like 1 or 2 half threads. So when you start a hole, you want to start off with the one that has the most, you know, your starting tap should have the most blunted threads coming up. That way it kind of helps self-center in the hole. And if you tried to start with a bottoming tap, you'd probably just break the tap off, or you wouldn't start it, or it'd be crooked. So yeah, knowing what you're getting is important, and also a little bit of kind of, I don't know, a little bit of attention to detail when you're actually using it. So there's lots of different ways. There's tools you can set on the surface that center your tap. I don't really have one, but I don't know. There's lots of different things you can do to help. You can also drill like this. You can have a puck that's drilled out that your tap will sit in nicely, and that helps kind of, you set that on the work surface and that locates your tap for you. That also really helps. I don't have one at this size right now, so I'm just going to do it by hand. But the biggest thing I would say is, also I need a smaller tap wrench. This is way too big of a tap wrench, but we're working with what we got here. So, yeah. If you don't really need anything to tap a straight hole if you are careful. So when you start it in, once you get like 2 threads in, you can't really change the angle of the tap, and if you have a crooked hole, you're going to have a crooked hole. But when you're starting, you come at this thing and you look in 2 directions. So you get it started. Your eyes are good at telling square. So if you look, make sure you're square in this direction, then you go 90 degrees to that. And you have to apply a little bit of downward pressure as you do it. Make sure you're at 90. Come over here. Again, we're applying downward pressure and we're keeping an eye on the tap. And just keep making minor adjustments, because right as you're first starting, you can minorly adjust what you're doing. Once you get a little ways in, the tap is set. The other thing too is watch out with how much pressure you feel building up on the tap, because if you, especially with a tap wrench like this, you can easily break a tap off if you apply too much pressure. So we're coming in, we're keeping an eye on that tap, just going real slow, checking both directions, making sure that we're still square. And for longer holes, it's better to set up a jig or use a drill press to center your tap for you using a spring-loaded punch. And there's lots of other methods, but for shallow holes in a plate like this, we should be able to get by with just eyeballing it. Again, just paying attention to where that's at. And now that we've kind of got going, we're starting to get to the point where it's set. And that's when I usually add a little bit of cutting fluid. I don't have a specific like Tap Magic or anything right now, but some WD works fine. And when you start cutting, you'll feel pressure build up, and then you want to back off. That breaks the chip, and then you continue moving forward, breaking the chip every so often, and you just work that tap through the hole. And these nice high-speed steel taps are just light years better than a cheap regular carbon steel tap. They last a lot longer, they cut a lot easier, and you'll really thank yourself, because I spent a long time with crappy taps before I discovered all of my grandpa's tooling that he bequeathed to me when he passed away. So now that we're through, just work it down a little bit, and then should be able to just back this out with our fingers. Then we're going to cut back over here to our tap box. A little bit of something right there. Probably your biggest mistake is starting with a crescent wrench, because it is really hard to distribute force evenly with the crescent wrench, and you'll get really wonky holes when you try to use the crescent wrench. So I spent a lot of time doing that as well. And we're going to look in our tap box. We're going to get our bottoming tap now. It's threaded the full length, so you can see it's got full-size threads all the way down. And we're just going to follow that first tap up, putting a little bit of cutting fluid on it. Get it started, put our tap wrench on, we're just working this guy through. Once we almost get out, just finished off our hand. So now we got that done. Take one of our bolts, got that guy in. If you take a look at that, it is nice and straight. So we're threading in real nice and straight. Threads are nice. So it's really not too hard to tap holes by hand, especially for little plate mounts like this. You just got to be careful and proceed slowly, and you'll end up with good results. So, alright, I'm going to take this guy, get this mounted on the lathe, and then get the motor on, and then we'll see if we can get the old lathe running. Alright guys, so we're back over here on the lathe. Got the new motor mounted, and the original calculations I did. So the original calculations we did were using a 2-inch pulley off of the motor, and this pulley over here that we got right now is a 3.5-inch pulley. So it speeded everything up a little bit, but we're still, kind of in our range here. If you look at, I got the digital tachometer here, so at our lowest speed setting, we'll shoot this guy. So we're at 245 RPM. So it's a little faster than I'd like. I was shooting for more like 100 on the slowest setting, but I think it'll be okay for now. I'm gonna buy a smaller pulley so that way I can go a little bit slower. But for now, for smaller stock, it'll work all right. And yeah, pretty happy with that. Got it all ready to go. I got a piece of stainless chucked up here. I got to get the steady rest set and get it adjusted and put in there correctly. But yeah, I'm gonna start on the new project with the chainsaw mill.